Good morning and everyone. My name is Parth Tyagi, and today I will be presenting my case study and simulation on the IBM Power Architecture. This presentation is part of my coursework for Manipal University, Jaipur. Let's begin with the overview of this powerful and influential processor family. Okay. The IBM Power, which stands for Performance Optimization with Enhanced RISC, also known as Reduced Instruction Set Computers, is a family of high performance microprocessor which was developed by the IBM. It is based on the RISC design principle, meaning it is used to reduce instruction set for faster and more efficient processing. The architecture is known for its scalability, parallelism, and reliability and has been widely used in servers, enterprise system, and supercomputers. So, in short, the Power family is built to handle demanding, data intensive workloads in both research and business environments. So, here comes the key features and design principles of my project. So, the IBM Power series is grounded with a RISC based design, which helps simplify instruction execution and improve the speed. It employs a superscalar design, means the processor can execute multiple instructions per clock cycle. It also supports out of order execution and simultaneous multithreading, which allows multiple instruction threads to run concurrently. Together, these features make the architecture highly scalable, efficient, and performance oriented, and it's suitable for multi core, server, and environments. Now, here comes the ISA, also known as Instruction Set Architecture. The IBM Power processor uses a fixed 32-bit instruction format which simplifies decoding and improves the performance. The architecture includes three main types: D type, X type, and B type. It supports immediate register index addressing modes, offering flexibility for different operations. Some interesting instructions include MADHD, which performs multiply and add operation on high double words, and sync, which ensures proper memory ordering in multiprocessor system. And these unique instructions help maintain data accuracy and synchronization across multiple cores. Now here comes the data path and pipeline. The IBM Power architecture features a deep superscalar pipeline with more than 10 stages in modern versions. It uses the out of order execution and branch prediction to maximize the efficiency. And separate execution unit handles integer, floating point, and load and store operations in parallel, which allows the processor to issue multiple instructions simultaneously, resulting in high instruction throughput. Overall, the pipeline and parallel data path design is a major factor behind power, high efficiency, and performance. Now, here comes the memory hierarchy. The memory hierarchy in IBM Power is highly optimized. Each core has a level 1 cache for instructions and data and a unified level 2 cache which provides quick access to shared data, and a large level 3 cache is shared among cores for high bandwidth communication. The architecture also uses a hardware prefetching and cache coherency protocols to reduce the latency. This design ensures fast and consistent data access, which is critical for large scale enterprise workloads. And here comes the specialized features and parallelism. Power processor excel in parallelism. They support multi-core and multi-threading processing, enabling high computational throughput. The Altivac, also known as VMX, provide SIMD capabilities, which means they allow a single instruction to process multi-data elements simultaneously. Additionally, PowerVM virtualization lets multiple operating systems run efficiently on the same hardware. And these specialized features make the IBM Power architecture ideal for AI workloads, cloud system, and high performance computing application. Now, the historical significance and comparison of this architecture. It has been a cornerstone of enterprise computing since its origin in the early 1990s. From IBM RISC system, it later evolved into a Power PC line, which was widely used in Apple computers and embedded systems. The Power processor have powered some of the world's fastest supercomputers, including the IBM Summit and Blue Gene. And when we compare it to Intel x86, The IBM Power offers greater scalability and parallelism, while x86 remains more dominant in consumer and desktop systems. In enterprise and scientific environment, however, Power continues to lead due to its reliability and multi-thread performance. Now, conclusion. So, in conclusion, the IBM Power architecture is a remarkable example of modern processor designs. It combines RISC efficiency with advanced parallelism and virtualization with scalability. From powering servers to supercomputers, Power continues to demonstrate high performance, energy efficiency, and reliability. As computing evolves towards AI and cloud computing, the IBM Power remains a vital architecture driving innovation in high performance systems. So, thank you for listening. This concludes my presentation on IBM Power Architecture and its simulation task. I hope this provide a clear understanding of its design, principle, performance, characteristics, and importance in modern computing. Thank you. Okay, so now here's the simulation of my code. So the program starts by setting up the variables and initializing the memory. Wait, so the program starts by setting up the variables and initializing the memory. For example, these lines. In these lines, here the memory location 0x24 and 0x25 are used to store the integer variable count, which is equal to 10. In other words, our program will generate 10 Fibonacci numbers. Here you can see this thing. अरे यार एक मिनट रुक जा. Okay, so now the program starts by setting up the memory variables and initializing the memory. For example, these lines. Uh, the lines are here. In this, we allocate the memory location to 0x24 and 0x25. They are used to store the integer variable count, which equals to 10. In other words, we can say that our program will generate Fibonacci 10 Fibonacci numbers. So now first we'll initialize the first two terms. Now these lines set up the first two Fibonacci numbers. Here, the first term is stored as 0 in memory location 0x26 and in 0x27. And the second term is stored as 1 in 0x28 and 0x29. The accumulator A is first cleared, which means it's set to 0, and then these 0 values are removed into the appropriate memory addresses. So now in these lines, where are the lines? Uh, yeah, yeah. So we are here. So these instructions prepare the call to print the function that prints the line, first 10 Fibonacci numbers. And the values are passed to printf using the registers R1, R2, and R3 before the long call, that is L call, is made to the function. Now we'll print the first two numbers. Uh, okay. Now this section checks if count is greater than or equal to 1. And if it is, it prints the first term, which is 0. A similar block follows the print that the second term, which is 1. Now this match the what happened in the C program where the first two terms are printed explicitly. Now from here we say okay. Uh, यार